Welcome to 3is Academy. In this video, we'll be looking at physics under the topic scalars and vectors. So let's begin. What are the objectives of this section? The students should be able to explain the concept of scalars and vectors. They must be able to explain the meaning of the resultants of two vectors. They must be able to resolve into a given direction, solve simple problems involving resolution and addition of vectors using analytical and graphical methods, and a host of others. So what's the concept of scalar? So based on our last session, we learned that quantities are divided into two types. We have the physical quantities and we learned that physical quantities are subdivided into two types. We have the scalar quantities and the physical and the vector quantities. So now we'll be looking at the concept of scalar, which is the scalar quantity. So many measurable physical quantities we encounter in our study of physics have only numerical values attached to them. Such quantities are completely described when only their magnitudes or size are known. Such quantities are completely described when only their magnitudes or sizes are known. So examples of such quantities are length or distance, mass, volume, density, time, speed, temperature, and energy. They are known as scalars or scalar quantities. So we refer to scalar quantities as the quantities that have only magnitudes. They are completely described when only their magnitudes or sizes are known. What do we refer to as magnitude? Magnitudes are also the sizes. For instance, let's take the quantity length as an example. So when we measure the length of a table, we say the length is 4 centimeters. So the 4 in that case is the magnitude, which is the size of the table. That's in the case that 4 is the magnitude. It's also a scalar quantity because it only has magnitude. That quantity, the quantity length, only has magnitude. So a temperature of 100 degrees Celsius is a number in some scale. It has no directional property. So now the scalar quantities are those which have only magnitude or numerical value but no direction. So when we measure the length of a table, we say 4 centimeters without including any direction to it. So that indicates that it's a scalar quantity. So the opposite of scalar quantity is the vector quantity. Also get to that very soon. So scalar quantities are those which have only magnitudes or sizes or numerical value but no direction. So examples of such quantities are length, mass, volume, density, time, speed, temperature, and energy. So you need to understand these quantities. So now, scalars are added by ordinary algebraic methods. Example, the addition of volume. So say for example, the volume of a liquid in a cylinder is measured, maybe we have 5 centimeter cube, and the volume of another liquid in another container is 10 centimeter cube. So how do we get the sum, or how do we resolve the two liquids? What do we do? How do we add them together? Scalar, because volume is a scalar quantity, so they are added by ordinary algebraic methods. So that is 5 centimeter cube plus 10 centimeter cube will give 15 centimeter cube. So we've actually determined the resultant of the two volumes. We've actually calculated it, which indicates that scalar quantities are added by ordinary algebraic methods. So a temperature of 100 degrees Celsius is a number is a scale. It has no directional property. So now let's look at the concept of vectors, which is the opposite of scalars. On the other hand, many other measurable physical quantities have both magnitude or numerical value and also direction as well. Let's take that again. On the other hand, many other measurable physical quantities, they have both magnitude or numerical value and also direction as well. That is, they have both magnitude and direction. Such quantities are not completely described unless their magnitudes and directions are specified. So these quantities are known as the vector quantities. So examples are displacement, velocity, acceleration, weight, force, momentum, and electric field. So we have lots of examples. So this is a few of the examples. This is a few of the examples we have. So vector quantities are those which have both magnitude and direction. So thus, a displacement is a distance measured in a specified direction. So one of the differences between the quantities distance and displacement is that distance is a scalar quantity while displacement is a vector quantity. So distance does not need to be specified with a direction, but displacement needs to be specified with a direction. For example, a bird flies a distance of 100 kilometers in a northeasterly direction. So that's known as the direction we've been referring to. It flies in a northeasterly direction. So velocity, while 100 kilometers here is the magnitude, this is the direction, the northeasterly direction. So supposing it was the distance we're finding, we would only write 100 kilometers. But since we are working with displacement, which is a vector quantity, we work with the magnitude as well as the direction. Velocity is the speed in a specified direction, e.g. a car travels due west at 90 km per hour. The kilometer per hour here, the 90 is the magnitude, while due is the direction it travels is the direction. So vectors are added by geometrical methods. Do not forget, we stated that scalars are added by algebraic methods, but vectors are added by geometrical methods. We can therefore distinguish between scalars and vectors by noting that whereas scalars have only magnitude or numerical value, but vectors have both magnitude and direction. We cannot specify a vector completely unless both its magnitude and direction are included. But we can describe a scalar completely by indicating only its magnitude, which implies that a vector quantity cannot be specified unless the magnitude and direction are a vector quantity cannot be completely stated unless the magnitude and direction are specified. But for the scalar quantity, it needs only the magnitude. It works with the magnitude. So also, whereas scalars are added by ordinary arithmetic, vectors are added by geometric methods. So now let's look at the representation of vectors. For vector representation, now since a vector quantity has both magnitude and direction, we represent such a vector by a straight line which has an arrowhead. So it is represented by a straight line which has an arrowhead. So here it is, vector is represented by a straight line which has an arrowhead. So this is it. The vector is represented with this by a straight line which has an arrowhead. So now indicate which has an arrowhead indicating the direction of the given vector. So the arrowhead here indicates the direction of the given vector. So now looking at the directions we have, we have the north. So we have the north, south, the east, west. So when we're trying to when we state that this body travels with a speed or with a velocity of 50 kilometer per hour, it travels with a velocity of 50 kilometer per hour in the direction. It travels in the direction of east. It's traveling to east. So how do we do that? Or we state that it travels 50 degrees east of north. Let's say 50 degrees east of north. There it is. This is how 50 degrees east of north is written. So if you want to state that a body travels 20 kilometers 20 degrees north of east, how do we do that? East of north, this is how it is written, east of north. What of 20 degrees east of south, we do this 20 degrees, okay, let's say 40 degrees east of south. This that is eating east of south. For west of south, you should know that this is it. So now west of south, so that is it. So now what I'm trying to point out is how the direction, the arrowhead indicates the direction. So now we stated that a body travels with a velocity of 20 km per hour, 20 km per hour in a direction 30 degrees east of it, 30 degrees east of north rather. So how do we do that? So here is the point. If it travels 30 degrees east of north, so it is like this, 20 degrees east of north. So how do we position it here? So we have northeast here, then this is it. It travels 20 degrees east of north. So the arrowhead here indicates its direction. So it indicates its direction. Degrees east of north. So the arrowhead here indicates its direction. So it's because the north and south are reference points. They are known as the reference points. The north and south are known as reference points. You notice that when this was illustrated here, the 20 degrees was attached to the north side, to the north direction. Is that it is attached to the northern direction. Why? Because north and south are the reference points. So then how do you now get this? The other one here, you say 90 degrees minus 20 degrees, which is 70 degrees. So what I'm trying to point out is that it is the arrowhead that indicates the direction. So now the length of the line is drawn proportional to the magnitude of the vector. Yes, that's actually correct. So when we are asked, when it is stated that it travels 40 kilometers, we need to draw the length of the line. We need to draw a line which will represent the 40 kilometers. So we don't just draw a random line. So but it is quite it's quite bad to now decide to draw a very long line. So there's a way we measure it. You can decide to say for every 1 centimeters, or for every, let's say, 2 centimeters, for every 2 centimeters of this, it is equal to 4 units. It is equal to 4. You know, the unit is also, let's assume we are representing 20 kilometers in this form. We are representing it with a vector. You can decide to say, okay, for every 22 centimeters is 4 units, and we are trying to get 20 units here. Okay, after this, after another 2 centimeters gives what? 8 units. So then we find a way to trace it. Okay, another gives what? That's 12 units. 12 units. Then another gives, then you need to increase it like this. Another gives, so until you get to a point. So another gives 16 units. Another 2 centimeters. Another gives what? 20. So that indicates that this is where we are going to draw the line of the vector to. At times it may not be longer than this. We can start to say, okay, from this point to this point, which is 4 centimeters, or let's say it is 5 centimeters, make it represent 1 unit. Then we don't need to draw a longer line like this. Or we could even say this point, which is 10 centimeters, make it 1 unit. Then another 10 centimeters gives what? 2 units. 10 centimeters, 10 units rather. So another 10 centimeters gives what? 20 units. Then definitely we've achieved the magnitude of the vector. So these are just illustrations to show us how they work. So the length of the line is drawn proportional to the magnitude of the vector. The arrowhead is always drawn so that it points in the direction of the vector. So for example, okay, now let's look at the addition of vectors. We stated that vectors are added geometrically, but scalars are added algebraically. So there's a way vectors are added. We don't just add with the manner of algebra. So now let's look at it. Addition of vectors. To add a speed of 10 km per hour to a speed of 30 km per hour. We merely sum up the two magnitudes to obtain a speed of 40 km per hour. Why? What's the reason? So this is because speed is a scalar. So we had it with the manner of algebra. So now, looking at this, here is it. Addition of speed 10 kilometers with 30 kilometers, it gives 40 kilometer per 40 kilometer per hour. So now, because vectors are quantities with magnitude and direction, they must be added in a special way. Simple arithmetic cannot be used if two or more vectors are not along the same direction. So now, let's get that concept right. So now, let us start with a simpler case of two vectors P and Q in the same direction. So we are trying to add two vectors which act on a body in the same direction. So their sum of resultants is given by R, which is P plus Q. So what it states is that, as stated earlier, a line and an arrowhead is used to represent a vector. So now when we have this as vector P, we have another body as vector Q, So when they act in the same direction, perhaps they are acting on a body, but they act in the same direction. How do we get the resultant? So we can be asked the question, how do we get the resultant of the vectors? What do? Because they are acting in the same direction, we add the two vectors together. Therefore, our resultant R is equal to P plus Q. Can you see the direction it acts and this one acts? So that's what is stated here. So the direction of R is the common direction of P and Q. So looking at this acts here, 5 newtons and 4 newtons, they act in the same direction. So the resultant R, which is the one here, is equal to 5 plus 4, which is 9 newtons. So suppose two forces P and Q of 5 newtons and 4 newtons respectively act on a body in the same direction. The resultant force or net effect of the two forces is given by this, which is 9 newtons. R is in the same direction as P and Q, but if P and Q are in opposite direction, so they act in different directions, then R is given by P minus Q. What does that imply? It implies that if this is the body and P acts in this direction while Q acts in this direction, P, to get the resultant of the vector, okay, so what do? We draw the resultant like this to this point here. Why? Because P is a vector of 5 newtons. The magnitude of this vector is 5 newtons and this is 4 newtons. So in vector analysis, it is the vector of greater magnitude, the direction of the resultant will lie, which implies that the direction of this resultant will lie with the greater vector. So anyways, how do we obtain the resultant of the vector? We say R is equal to 5 minus 4 newtons, because they are acting in different directions, which is equal to 1 newtons. So that is it. Since P is greater than Q, R is in the direction of P. So now, exercise. Suppose a body walks a distance 2 km eastwards to a point A, and then walks another distance 4 km westwards. Its displacement from a starting point is given by what? So how do we solve the kind of the question? How do we solve it? Now looking at this now, let's analyze it. Suppose a boy walks a distance 2 km eastwards. So the boy walks 2 km eastwards, and we know where the east is located. The east is located at the right side. So the boy walks 2 km eastwards. okay, suppose the boy walks a distance 2 kilometers eastwards to a point A. So it walks to a point A. It the boy walks to a point A and then walks another 4 kilometers westwards, and then walks, looking at this here, we have it here. So and then walks another distance 4 kilometers westwards. So then walks another kilometers westwards, is located downwards, which is 4. So this should be longer than this, so we need to obey that rule. So let's erase this a little bit. So the 4 kilometers should be longer than that. So 4 kilometers westwards. Now his displacement s from his starting point is given by, so what we are asked to calculate is his displacement s from his starting point. So what we are going to do now is to obtain the resultant of the vector. We are asked to obtain the resultant of the vector, so we don't just add algebraically as we've done before. So we are going to apply the Pythagoras theorem. Why? So now let's look at this. Okay. Okay, now how do we solve a question like this? Oh no, we need to understand something. So suppose a boy walks a distance 2 kilometers eastwards to a point A. Okay, here it is. So let's solve this question again so we can understand the concept. It walks 2 kilometers to a point A. Okay, this is it. 2 kilometers to a point A eastwards, and then walks another distance 4 kilometers westwards, and then walks another distance 4 kilometers westwards. So what this implies is that we are not going to continue drawing the vector from this point. We are going to start from this point here. It's very important. So that was actually a wrong approach I took. So now what we are going to do is solving like this. After walking towards the east, then what? Walks another distance 4 kilometers westwards. This word another is very important in this statement. The boy walks another distance 4 kilometers eastwards. So what we are doing is what? Walks another 4 kilometers like this east westwards. So that was, I'm very sorry, the direction here was the south. That was actually a mistake. So we have the north here, the south, the east, and the west. So this is it here. 4 kilometers. So this is actually a very simple question. It's actually, so what do we do? How do we get the resultants? We have to find the displacement from the starting point. So how do we do that? We say the resultant, which is the displacement, which is also the displacement, is what? What do we do? We subtract, because they are in opposite directions. So 4 minus 2 is equal to 2 kilometers, which is the resultant of the vector. So now let's move to another aspect. Vectors inclined at an angle to each other, because the ones we have been treating is the vectors acting on a straight line. So we'll be moving to the ones that are inclined at an angle to each other. Simple algebraic addition or subtraction cannot be used if two or more vectors are inclined at an angle to each other. For example, suppose a man starts from A and walks 3 kilometers eastwards. So now let's look at this diagram here. Suppose a man starts from A, he starts from A, here is the point, and walks what? 3 kilometers eastwards. He walks 3 kilometers eastwards, which is here, and then 4 kilometers southwards. Then walks 4 kilometers southwards, which is here. His motion can be represented graphically using scale drawings. His motion can be represented vertically using scale, can be represented graphically using scale drawings. So what does this refer to? It is stated that the boy walks 3 kilometers. Okay, the boy starts from A and walks 3 kilometers eastwards. So the boy starts from A and walks 3 kilometers eastwards. This is 3 kilometers, and then walks what? How many kilometers southwards? 4 kilometers southwards. 4 kilometers southwards. Okay, and so his motion can be represented graphically. So what this implies is that how do we resolve this vector? So what are we asked to calculate? So let's look at that again. Okay, we have to get the resultant of these vectors. We have to get the displacement of the vector. So using scale drawings as shown, AB represents a displacement of 3 kilometers east and BC represents displacement of 4 kilometers south. By proper choice of scale, we can obtain that its resultant displacement is 5 kilometers. So now how this has been done is that, looking at this here, when we are adding two vectors at right angle to each other, draw a line from this point to this point here. This line that is drawn here is known as the resultant vector. That's the resultant vector we are actually searching for. So now let's give this B and C. It's known as the resultant vector. So now it's known as the resultant vector. So how do we work with this? Now when we are asked to calculate the resultant of a quantity, whether we have to calculate the displacement or any other physical quantity, any other vector quantity, what do? We ensure we get the magnitude as well as the direction. Get the magnitude as well as the direction. So now how do we now obtain the magnitude from here? Supposing it was the two vectors were acting on a straight line, it would have been 4 plus 3 or 4 minus 3, but now they're acting at right angles to each other. So now for the direction first, okay, for the magnitude first, this is going to be our magnitude. We need to obtain the value of this line, the size of this line, which is going to be our magnitude of the resultant of the vector, which is also the line drawn from this point A to this point C, from the starting point to the end point. But how do we get the direction? The direction is gotten by specifying an angle somewhere. Specifying an angle somewhere which will be inclined horizontally. So now what I mean is, the angle we are specifying must be inclined to a line horizontally. We are trying to get the direction of the vector. So now looking at this, if I decided to add an angle here, let's say this is the direction we need to get. This angle acts to the vertical. It acts to the vertical. That means this is absolutely wrong. We cannot specify our angle here. So where do we now specify our angle? There are series of places we can specify the angles. I can decide to draw a symmetrical line here and here to do that. But to avoid confusion, let's just leave it like this. So now where do we specify our angle? We can't specify the angle here because I just received a response that the angle will specify there. No, because this is definitely a right angled triangle. So we can't do that here. This is a default right angled triangle, so we can't specify the angle here. So for those of us that have made that mistake, it will be recommended for you to move to the mathematics section and watch a video on trigonometry so we can understand better. So now let's proceed. Where do we specify the angle? We can specify the angle here because this angle acts to the horizontal. This is an horizontal surface. It acts to the horizontal. Yes, you're actually correct. So we cannot specify the angle here. So allow me erase this one here. So now we are good to go. We can now solve with the use of the Pythagoras theorem, using the formula that the hypotenuse square is equal to the opposite square plus adjacent square. So based on our knowledge of Pythagoras, we know that this from this point to this point is the hypotenuse. H is from this line here to here, and the opposite is the angle, the side that faces the angle, which is this one here. the opposite hypotenuse, and the adjacent is the remaining angle here. So how do we do that? We say hypotenuse square, which is r square, which is equal to the opposite square, which is BC, hypotenuse, which is BC square, plus adjacent square, which is AB square. So r square is equal to BC is equal to 474 square, and AB here is 3 square. So 4 square plus 3 square gives 16 plus 9, which gives us 25. So r is definitely equal to the square root of 25, which is 5 kilometers. So we actually got in the value of our magnitude. Then the magnitude is equal to 5 kilometers. Now, but when we are working with vectors, it's incumbent on us, it's mandatory of us to specify the direction. So how do we specify the direction? So we actually gotten where the direction is, then you can make use of the pattern, the trigonometric ratio as well. So by saying what? Now, if this is the adjacent and opposite, when we refer this to the SOHCAHTOA, we have SOHCAHTOA. We have the opposite and adjacent. So let's look at this. Which of them have opposite? Which of them has the opposite and adjacent? This has opposite and hypotenuse. This has adjacent and hypotenuse. This has the opposite and adjacent. So we are definitely using TOA. Then we say what? Tan of this angle here, tan angle is equal to the opposite, which is equal to 4 kilometers, which is the angle that faces the side that faces the angle, opposite over the adjacent, which is what? 3 kilometers. So how do we get to say angle is equal to the arctan of the tan inverse of 4 over 3 to get our answer? So now that's definitely our answer. Looking at this here, so where is it? So now looking at this, we have this which has been stated here, and we have the tan angle of, that's the inverse tan of 1.33, which gives this. So here is the value of the direction. So our answer now is 5 kilometers, and the direction is definitely 53.13. So now let's move to the resultant vector. So questions will be dropped at the end of the video, so we can solve and send the questions to the email account of to the following email address, to email account hsani507@gmail.com. So now let's proceed. The resultant vector. Now, the resultant vector is that single vector which would have the same effect in magnitude and direction as the original vectors acting together. The resultant vector is that single vector which would have the same effect in magnitude and direction as the original vectors acting together. So that's what we've actually been working on since. So now let's look at the parallelogram method. So we've actually learned how to get the resultants of vectors that act on a straight line. We've learned how to get the resultants of vectors that act at an angle. We are now going to learn how to get a vector, the resultants of vectors that are acting they are inclined with an angle that is not equal to 90 degrees. That means they could be acute or obtuse and so on. So now there are in general two methods of adding or compounding vectors to find the resultant. These are the parallelogram method and the triangle method. The parallelogram method, the resultant of two vectors inclined to each other may be represented by the diagonal of a parallelogram drawn with the two vectors as adjacent sides. In this method, the two vectors are drawn from a common origin and a parallelogram is constructed using these two vectors as adjacent sides. The resultant is the diagonal drawn from the common origin. So what does it state? Now let's look at the parallelogram law of vectors before we proceed. So the parallelogram law of vectors states that if two vectors are represented in magnitude and direction by the adjacent sides of the parallelogram, if they are represented in magnitude and direction by the adjacent sides of the parallelogram, the diagonal of the parallelogram drawn from the points of intersection of the vectors represents the resultant vector in magnitude and direction. What does this imply? Now looking at this, let's erase this. If two vectors act what? States that if two vectors are represented in magnitude and direction by the adjacent sides of the parallelogram, that means they act like this. Adjacent sides of the parallelogram so we'll be working with vectors that are acute, obtuse, and so on. What happens? It is stated that, okay, let's assume this is a vector P, this was vector P, and this was vector Q. So what happens? The diagonal of the parallelogram drawn from the points of intersection of the two vectors represents the resultant vector in magnitude and direction. So the diagonal of the parallelogram drawn from the points of intersection of the vectors represents the resultant vector in magnitude and direction. It implies that so the diagonal of the vector drawn from the points of intersection of the two vectors represents the resultant of the vector. So for us, we can do this here. So for us to get the resultant of this vector, is actually required of us to draw a line from the point of intersection to this here, which is also the diagonal of the parallelogram from the point of intersection. So here now is the resultant vector. This is the resultant vector. So that's it, parallelogram laws of vectors. Now, exercise. Now let's take an exercise under the resultants of vectors acting at acute angles, obtuse, and so on. So which will fall under the parallelogram, laws of vectors. Now, find the resultants of two vectors of 3 units and 4 units acting at a point O at an angle of 45 degrees with each other. So find the resultant of two vectors of 3 units. Again, the first exercise. Find the resultant of two vectors of 3 units and 4 units acting at a point O at an angle of 45 degrees with each other. We have to find the resultants of two vectors of 3 units and 4 units acting at a point O at an angle of 45 degrees with each other. So how do we do that? Now let's take the question. Let's solve it. So let's erase this. The vectors act how? So the resultant of two vectors of 3 units and 4 units acting at a point O at an angle of 45 degrees with each other. So the vectors act at 45 degrees with each other. That means that the angle between the two vectors is 45 degrees. So now, supposing this was the first one and the second one. Oh, sorry. Let's take a very good straight line. Okay, of 3 units and 4 units. So another is there is something very important you should also note. You would figure that we have the vector of 3 units and 4 units. So in vector analysis, it is the vector of the larger magnitude that stays at the bottom. It is the vector of larger magnitude that stays at the bottom. So now that implies that the one of 4 units stays at the bottom like this. So this is a 3 units vector. and this is the 4 unit. So now let's proceed. The arc has angle of 45 degrees, sorry, like this, 45 degrees to each other. So acting at a point O, so we need to include that as well. They act at point O, vectors, okay, with each other. So now let's label our diagram. We have this will be A. You can give this. Oh, this should be this should be properly drawn. The head is very important, which is the pointer to the direction. So this is, let's give this B. So now what do we do now? We also find the resultant of the vectors, which implies that we get the magnitude as well as the direction. We get the magnitude as well as the direction. And do not forget, under the parallelogram laws of vectors, it is stated that it is the diagonal drawn from the point of contact, the point of intersection of the two vectors, represents the resultant. So now let's assume this is like this. We have this one here. Then this is definitely the resultant vector. The resultant vector. So what we need to do is to get the value, the magnitude of this line. Then we are actually gotten our magnitude. Then just remains the direction now. So let's do that now. How do we solve for the magnitude? Now we find out that this one here, this 3 units is also the same as 3 units here, because it's a parallelogram, so they are equal. And 4 units here is also 4 units here. The opposite sides are equal. So now how do we solve a question like this? So now let's extract the diagram from this point. Let's extract this part out and say this O like this. You can actually straight it out like this. Okay, that's okay, correct. Or let's reconstruct it well. Now you can actually do this. Okay, sorry, let's use the red one. So now we have the resultant here. We have vector of 3 units here. We have the 104 units here, and we have our angle here, which is definitely the angle that is here. Is not actually equal to 45 degrees. So now, how do we get the value of this angle? What do we do to do that? No, looking at this diagram, looking at this wall diagram, the parallelogram, we can actually get the angle here. You can get the angle here, but this is an angle. You can get the angle there. How do we do that? When this line is extended like this, when this line extended, now for example, based on our knowledge in working with corresponding angles, we find out that 45 degrees here corresponds with 45 degrees here. It corresponds with 45 degrees here. So this angle here, this and this, they are corresponding angles, so they are equal. Now then how do we now get the angle here? How do we get it here, the remaining angle here? We say 180 minus 45, because this results to the sum of angles on a straight line, which is 180. If the sum of the angles is 180, then to get this we say 180 minus 45, and 180 minus 45 should give us 135. Should give us 135. So that means the value of the angle here is 135 degrees. So that's how we're working them out. When you are giving questions like this, they will actually put that here 135 degrees. That is it. So now we can actually get the value of how, using the cosine rule in math. Using the cosine rule, we use the what, the cosine rule, the cosine rule. We use the cosine rule, which is now how does the cosine rule state? So now let's look at the formula here. It's stated, or is it stated here? Okay, I think it's not well explained here. So now let's give a better explanation here. The cosine rule states the largest size here, which is the angle in the side here. We'll be working with the side here, which is r square. So let's give this O. Since this is O, we have C here, then this is definitely C. Then for the cosine rule, the formula goes by the OC square, which is what? OC square. This is this side. The R square is equal to the two sides, the squares, the addition of the squares of the two sides, which is what? O, let's say this is B, okay, this is definitely B, which is OB square plus BC square. OB, this is O, OB squares plus BC square. So how do we solve it? OC is R. So I'm sorry, we are not through with it. I'm very sorry for that. So OC square, which is OB square, this is OB, plus BC square, minus, for the cosine rule, so I'm writing the formula for the cosine rule, minus what? These two sides, OB times BC, 2OB, this is 2OB times BC times 2OB times BC, cos the angle here, cos OC, cos OC implies that what? It implies that cos OC, which is the angle here, OC, the side, the angle that faces the side, which is 135 degrees. So what do we mean? The cosine will state that what? That we are definitely looking at this OC square, which is the cosine rule, R square, because this is actually a default formula. This formula is default. You say R square is equal to the OB square, which is 4 square, plus what? The BC square, which is the 3 square, minus 2 times 4, 2OB BC, 2 times 4 times 3 cos OC, which is 135 degrees, cos 135 degrees. So we actually have to solve this. Having solved that, look at it, get 9 plus 16, is it 16 here? Okay, yes, 9 plus 16, which is the squares of this, plus 2 times 3 times 4 times this, cos 135 is also equal to 0.0701. So you get 6.48 units. Then the resultant is equal to the 6.48 units. 6.48 units. So now what we have actually gotten now is the magnitude only. Is the magnitude, which is 6.48. So now how do we get the direction? In a parallelogram of vector, the direction is located here. Here, not this, just this. So how do we get it? So let's assume this was the direction. Looking at this, we make use of the sine rule for that. We make use of the sine rule to get the direction. So how do we do that? We say sine theta, sine this angle here, over the sides, which is 3. That's what faces the angle. For the sine rule is equal to is equal to the sine of the other one over that. So is equal to the sine of this of 135 sine of that angle over what, you should know that the side it faces, which is r, and we've gotten r as 6.48. So how do we solve it? So we say we cross multiply and get the answer, then definitely the angle is equal, what do we have here? We have the, okay, let's look at this one here. Okay, over BC is equal to sine 135 degrees over OC. Okay, that's actually possible. So when we solve it, we get theta this, then theta angle, the direction is 19.11 degrees. Then definitely that is our answer. This is the magnitude and this is the direction. So you can watch this part of the video again to get it right well. Now let's proceed. Okay, so let's take these 3 questions as our assignment. So you are expected to submit to hsani507@gmail.com. So, and send more questions when you are able to, when you are unable to solve some of your questions. Thank you very much for watching. Please like and subscribe to this channel if you enjoyed the video. So thank you very much.